Hello, everybody. How are you? Good to see you again. I see that I clicked the logo button a little bit too early. But in any case, welcome everybody, and welcome to our daily live stream, Ask Math Anything. And as people noticed, I did indeed try not to be late. That's because I'm trying to practice. As some of you may have noticed, we have made an announcement on the live stream page. And next week, Wednesday, Thursday, and Friday, we're actually going to all have next week, Wednesday, Thursday, and Friday, we're going to have an official collaboration with Math Counts. Math Counts is the biggest middle school math competition in the United States. And what Math Counts does is it normally has all these fun contests where people come together to do hard problems. And next week, Wednesday, Thursday, and Friday, we're actually going to have a discussion of the solutions to this year's chapter round problems. But given that lots and lots of people are going to come to attend that, I guess I need a bit more practice being on time. So I was so proud of myself. I even started the logo before time. Oops. In any case, if you're new to this live stream, I want to welcome you. What we do here is we don't have a math class. In fact, what I do is I try to find out what people are interested in. And based on what people are interested in, I'll go and make a mini lesson improvisationally about that topic. So the whole point here is to go and find out what kinds of things people want to learn about. And when I see that, I will always try to find a way to explain it in a way that uses just algebra or geometry. In that way, I'll often be skipping over questions that are a bit more advanced in mathematics. If you want to see more of that, the more advanced questions we might save for things like the online class that we actually also run. Okay. Well, if you've been here before, you know what to expect. In fact, if you've been here before, you're somehow noticing that my shirt is a darker shade of blue than usual. And it is true. Somehow, when I reach into my closet to pull out a shirt, there are all these different colors once it becomes short sleeve weather. Let's see. What should we talk about today? Ooh, that's interesting. Annie Wu asked, how do you put infinity in a finite question? That seems like a very interesting philosophical question. So if it's a finite question, could it ever use infinite things? Well, the thing that comes to mind right away, that I think of right away, is just something like 0.99999 repeating. Now, on the one hand, it looks like it's going on forever. Wait, you can't see anything. Let's go and fix that right now. If you can't see anything, then why is that? Now it's problem solving time. Something is not connected all the way into our system. So let's go and see what's going on. Oh, that's interesting. Oh, it seems to think that this is not plugged in. Let's try again. It still seems to think this is not plugged in. I'm going to go and check out where the other end is. I'll be right back. For some reason, it does not like this cable. We're back. All right, so here we are. We're back here with sound. Is everyone able to hear again? Yes. And now, actually, the pen's over there. Great, good to see you again. Right, so the reason why that happened, if you're curious what happened with the sound, it's because yesterday evening I was actually getting interviewed, and we used the same equipment in the studio to do video interviews for appearing in newspapers, or well, newspapers don't have videos, but for appearing in various media publications. But back to this. Right, so we were talking about can infinity come into, oh, people said the sound is lower. Well, that's easy to fix. The question was, whoa, that's too loud. The question was, can you have infinite things in a finite question? And what I wanted to hit is that, you could write something like 0.9999999, and that is an infinite thing, but the answer is still finite. The answer is actually still 1. So that's one way that you could see infinite things in a finite question. Another way that you could see infinite things in a finite question might be, oh, now it's too loud, people say. We'll play the Goldilocks game. Right, the other way that you could have infinite things in a finite question can be that somehow it's possible for things to get really, really big when you put in things that are not that big. And the best way to think of this is actually graphs. So I'm going to graph something. Another place that we would see something like this is if I want to graph, for example, what if I want to graph y equals 1 over x minus 1? So this is something which, I'm just going to put in some normal number x, and I see what comes out. I see what number comes out for the y. Now, if I put in a number x, which is like 2, that's not very interesting. If I put x in, which is 2, then what comes out is 1 over 2 minus 1, which is 1 over 1. That's there. And if I put in x equals 3, if I put in x equals 3, then y equals 1/2. So x equals 3 is over here, and 1/2 is half of that. So this doesn't look so interesting, right? I mean, if x equals 4, it's 1/3. And in fact, you can connect all of these together, and the graph just seems to be fairly boring. You can put in things, and somehow as you put in these things, you get other numbers. You put in numbers, you get other numbers. Other numbers aren't too big. But of course, why I didn't draw out this side is because it turns out that if you try to plug in numbers that are close to 1, this thing blows up. That's in fact what we call it. Aha! So Tiger Lee wants me to plug in 1.00001. Well, you see, if I plug in something that's just a little bit bigger than 1, then I get something enormous. It does this. So it actually goes all the way up to positive infinity, very, very close to 1. And so that's the main reason why, that's an example of something which can get really, really big in a finite problem. And somehow I'm putting in a very small finite number, but the answer is huge. It's also kind of fun, because if I go the other direction, if I put in a number x which is just less than 1, then I get a number which is like negative infinity. Well, I mean, it's very, 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 very negative. And so the graph looks like this. So the answer is that yes, you can actually get things that get infinitely large with just putting in a finite thing. Okay, what other questions can we get here? Let's see. No name says y equals 1 over x is another example. In fact, those are all the same kinds of examples. 1 over x and 1 over x minus 1 are very closely related. In fact, if I want to know what 1 over x looks like, I just take this whole picture, and I'm going to cheat. Let me show you what x equals, let me show you what happens if I want y equals 1 over x. I just erase that part, and I do this. You can't really do this with a chalkboard, but it works well. It works well with this computer equipment. If I draw this, this is y equals 1 over x. And here my numbers are that this is 1, and this is 1, and this is 2, and this is 3, and so on. In fact, whenever I do something where I have like a y equals 1 over x, or y equals 1 over x minus 1, all I have to do is I have to shift back and forth. And the reason you shift back and forth, you can think of it this way. It's like if I have 1 over x, or 1 over x minus 1, x minus 1 just means that it gets to a certain number one step more slowly, because I do minus 1. Okay, what is the question? That's what I want to find out. I want to find out what we're going to talk about next. Ellen Wei asks, why is 7 so special? 7's a very special number. You see, It turns out that if you go and ask a person, tell me a random number between 1 and 10, the most common number that people think of is 7. Because somehow people don't want to tell you 5. 5 doesn't sound that random, you know what I mean? Random number between 1 and 10. Almost nobody tells you 1 or 10. And a lot of people just choose 7 because it seems like it's lucky, or it seems like it's unusual enough. It's a strange human psychology. We're somehow attracted to the 7. Now, if I want to say other nice things about 7 though, I can tell you that one reason why 7 is nice is also because, well, it's not nice, but it's the first prime number that it is very hard to tell whether a number is divisible by it. You know, if I want to know if a number is divisible by 2, what do? I look at the last digit and I go and see if it's even. There's also a way to find out if a number is divisible by 3. You try adding up all the digits and seeing if the sum is divisible by 3. Divisible by 5, the same thing. But divisible by 5 is looking at the last digit. That'll be good enough. But if you want to know if a number is divisible by 7, it's no fun at all. So 7 is also unusual in this way. It's like the first one of these prime numbers that is not very nice to play with. There's actually also a trick for divisibility by 11. So 7 is this first weird number. Also, another nice thing about 7 is that 1 over 7 has a nice decimal representation. If you take 1 divided by 7, we've done this before in a bunch of my online classes, but I'll just do it real quick. It's fun. If I do 1 divided by 7, 7 times 1 is 7. Oh, I shouldn't have written so big. 34, 28, 22, 14, 8. That's a weird 8. 8. I ran out of space. Oh no. 45, 35, and perfect. 7. And if I put down what was next, I would get 49. I subtract, I get a 1, and it repeats. It'll just repeat with 0.142857. And that's also kind of fun, because this is the first super long repeating pattern that you see when you divide by numbers. Okay, what should we do next? What question should we do next? Okay, here's a fun question. Somebody said, can you talk about reverse psychology? The reverse psychology is a funny thing, where if you have a question, the question is one where you sort of think that you should know the answer, but maybe you don't because there's somebody trying to psych you out. Let me give you a very specific example. And this example comes from the International Mathematical Olympiad. And the International Mathematical Olympiad is the toughest contest in the world for high school students in math. So this is the International Mathematical Olympiad math problem. International Math Olympiad. That's not how you spell Olympiad. Olympiad. It was in the year 2010, and it was problem number 5. Okay? And by the way, the International Math Olympiad has 6 problems. Problem number 5 counts as a pretty hard problem. But the question I can explain to you guys is quite simple to understand. It's like this. You have 6 buckets. And some of you may have seen this on one of my other YouTube videos. If you haven't, I'll encourage you to go and check it out. It's one of my YouTube videos. It talks about this in great detail. And today I'm only going to give a very, very brief overview. I have 6 buckets here. And each of the buckets has 1 coin in it. This is a coin. So I've got these coins. I have 6 coins. And actually we can think of them as pennies, right? Let's think of those 6 coins as pennies. Each one of them is 1 cent. Now, these are magic buckets. You're able to go and touch a penny, and when you touch the penny, it disappears. But then 2 pennies appear in the bucket to the right. So there's something that you can do. We'll call it magic A. It's called A because there will be a magic B. But magic move A, what you can do is you can touch a penny, it disappears. And after it disappears, 2 more pennies appear in the bucket to the right. Okay, so if I touch this penny, poof, it's gone. But then 2 more pennies appear in the bucket to the right. And I can do this as many times as I want. I can keep like touching more pennies and poof, more pennies appear. So, I can touch this one, that's gone. And now there are 2 more pennies over here. And by the way, do you know what happens if you touch this last one? It just goes poof. And there's no bucket on the right, so there's nothing else that happens. So actually touching this is just called throwing away money. Don't touch any pennies in the rightmost bucket. Okay? So that's how this works. It is a very simple game. You can touch a penny and it goes poof and 2 more appear to the right. And there's a question. Does anyone know how much money you could possibly make? When I say money you could make, at any point you can say, I'm done. I just want to take all the pennies. Does anyone know how much money you can make? What's the most number of pennies you can make? This is not actually the IMO problem. This is an easier version. What's the most number of pennies that you can make? Does anyone know? Well, 68 cents. Somebody thinks you can make 68 cents. Or maybe I just can't read because my vision is not good enough. How is this possible? That's true. This is a magic problem. It's not really that you can do this in real life. But the question is, you start with 1 penny in each of those buckets, right? There's 6 buckets. Each of them has a penny. And you go and touch a penny and it goes poof. And then 2 more pennies appear on the right. And then you can go and touch one of those. That one goes poof and 2 more go on the right. And it just keeps going on. Can you really get infinity? It's not really infinity, right? Because as you're touching them, the pennies are kind of going to the right. I see a bunch of people saying the most common answer I've seen so far is either infinity or 63. And I'm telling you it's not infinity, because as they get over to here, if you touch a penny in the right, it just goes poof. And there's no more, because there's nothing else on the right. So a bunch of people think the answer is 63. Why is it 63? Well, it's 63 because you can think of it this way. It's like every penny that's in the last bucket is worth 1 cent. Are you ever going to do anything else with it? No, it's just going to stay there. Any penny that's in the second last bucket, that's worth 2 cents. Because any one of these pennies, if you touch, it turns into 2 of those. Does that make sense? Hopefully it makes sense. It should make 2 cents. Oh, that was a bad joke. Anyway, so any penny over here, if you have a penny in this bucket, you touch it, it goes poof, and you get 2 here. But each of these was worth 2 cents. So then how much is a penny in this bucket worth? Does anyone know? Oh my gosh, you guys are hilarious. Very punny. You guys outdid me on that one. Yeah, this is worth 4. Right, so let me write down some things. Every penny here is worth 1 cent. Every penny here is worth 2 cents. Every penny here is worth 4 cents because I could turn it into 2 cents. And if I keep going, any penny here is worth 8 cents. Right? And you just keep going, and over here, each one of these is worth 16 cents. And each one of these is worth 32 cents. So if the question was asking at the very beginning, if I have 1 penny in each bucket, how much is this worth? Well, it's worth 32 plus 16 plus 8 plus 4 plus 2 plus 1. We've done this kind of problem before. Adding up these powers of 2 gives you the next power of 2 minus 1. And so the answer is 63 cents. But that's not worthy of an International Math Olympiad problem. The International Math Olympiad problem went one more step. It said you have 2 kinds of magic. That was magic A, but there's also a magic B. Magic B works like this. Let's suppose I did some magic A already, okay? I did some magic A, it did this. This is what I got so far. Magic B, the way magic B works, is you can touch any penny, it will go poof, no more penny, but then the next 2 buckets are going to swap. Okay? So what you can do is you can touch a penny, and then it will disappear. It disappears. and the next two buckets swap. What does swap mean? Well, let's give an example. I'll touch this one, poof, it's gone. But then when it's gone, okay, it needs to look more gone. When it's gone, then the next two buckets are going to switch. So previously it was empty and 3. Now it becomes 3 and empty. Does this make sense? So what you can do is you can touch one and you can swap. If you touch one of these buckets too close to the right side, it's bad. If you touch this one, it'll go poof, and there's nothing to swap. So it just goes poof. If you touch this one, it'll go poof, and there aren't two buckets to swap. So it'll just go poof. That's bad. That's wasting money, right? That's throwing away money. So don't touch these buckets, pennies in the last two buckets if you want to use magic B. So now you've got two kinds of magic, right? You can use magic A, you can use magic B, you can use magic A again. Let's go and touch this one. Poof. And it made 2 over here. And let's do it again. Let's go and touch this one. Poof. And I get 2 more over here. This is great. I'm getting rich. That should look like a bigger penny. Okay? I'll touch this one again. Poof. Look at all this money. So, I can do this a whole bunch of times. I could also go and try to do a swap again. Oh, let's touch this one. Poof. And I get to swap the next 2. And that's stupid because they're both empty. So I just wasted money if I touch that. But I'm just explaining you can do magic A, magic B, more magic A, more magic B. All right, back to the question. What's the most number of pennies you can make? Does anyone think you can make more than $1? Does anyone think you can make more than $1? How much money do you think you can make? I don't expect an answer here. I don't expect anyone to actually know the answer. I'm actually just curious. What do you think? You have a chat. You can type in. How much money do you think you can make with both magic A and magic B if you get to decide? Obviously, you can make at least 63 cents because we can make 63 cents with only magic A. But a lot is not really an answer. And the answer is not infinity. You cannot make infinity because as you touch these things, the pennies kind of move to the right. And after a while, they run out. So the answer is not infinity. Rainbow Chang has seen a math talk about this. This is a famous problem. Wow. Daniel Miller thinks he can make $15 million with this. You start with 6 pennies. Very interesting. So, quite a lot, 15 million. Use a claw to move the pennies. Oh, you guys are funny. So you don't actually touch them, right? Somebody says $2, 12. Okay, we get a bunch of different answers right here. This is a lot of, oh wow. Mellow Yellow thinks you can make 69 trillion pennies or dollars. Doesn't matter, it's still a ton of money. 5. Okay, we've got a lot of different answers coming in here. Some of them are huge. Wow, look at that. Crazy Vishnu. That's a crazy number. 100 septillion. 1 trillion. People seem to be liking big numbers here, right? Lots of big numbers. Melt all the pennies and sell all the copper. That might be worth more. They supposedly say that if you melt a penny, the copper is worth more than 1 cent. But we can see all these different answers. We see Jacqueline Zhou has gone for 1,000 decillion, right? And the answer is not infinity. Oh, finally, a Google showed up. Hao Lin Yuan said a Google. You think you can make a Google pennies? Wow. That seems to be the biggest number I've seen so far. 10E99. That's also 1 Google. Melting pennies is illegal. That is correct. Okay, now we see we have Googleplex, 1 Googleplexian. We have some pretty big numbers. Actually, what's a Googleplex? We got a big number already. A Googleplex is 10 to the power 100. It is 1 with a Google zeros. A Google is 10 to the power 100, which is 1 with 100 zeros. So we have some pretty big numbers, okay? Great. Now that we've seen all these numbers, this seems like one of the ones that people were like, that's just a huge, ridiculous number. There's no way that's the right answer. That's just a huge, ridiculous answer. I should now tell you what the IMO problem was. The IMO problem didn't ask you, what's the most number of pennies? No. It actually asked you a true-false problem, true-false question. It was a yes or no. Can you make 2010 to the 2010 pennies. Actually, oh, you guys already Googled the problem. It wasn't even just 2010 to the 2010. It was 2010 to the 2010 to the 2010. So this is a true-false question. It's asking you on the International Math Olympiad, is it possible to make 2010 to the 2010 to the 2010 pennies? Wait, by the way, that's bigger than this ridiculous number that nobody thought was going to work. You know, like whoever said a Googleplex was not serious. They were just being like, hey, everyone's saying a lot of big numbers. Let's have fun saying big numbers. But the answer is probably like you can make $10. But this is now the International Math Olympiad problem. It's asking you, can you make that much? Now, people who came late, the question was reverse psychology. Can I give an example of reverse psychology? So here's the example, right? So you look at this problem and you say, when you're doing it, you say, that number, that's too big. There's no way it can be 2010 to the 2010 to the 2010. So if you're a student, you say, I should find a way to disprove it. In the IMO, you can't just say yes or no. You have to explain why. So you go and say, okay, my goal is going to be to show that you cannot make that much money because it's ridiculous. It's like way too much. But then the IMO student says, oh, no. But that would be too easy. You see, this is the International Math Olympiad. They would never ask us a question where the answer is obvious. Therefore, the answer is obviously you can, right? Because it would look like you obviously can't. But since this is the International Math Olympiad, surely it's a trick question. And so the answer must be, yes, you can make this much. But then the International Math Olympiad student says, no. That would still be more like a normal school test. In a normal school test, they would put this as the trick question at the end. But this is the International Math Olympiad. So clearly, it's a trick question. So you can't make this much. Because otherwise it would just be obviously a trick question. And then as Eric Feng is seeing, this is becoming infinite reverse psychology. Because then you go like, no. But that would still be too simple. This is still International Math Olympiad level. So that means you can make this much money. And after a while, you just go nuts. Because you're reversing your psychology, and you've lost track of what you're actually trying to prove or disprove. And it turned out that year on the International Math Olympiad, this was the hardest problem. The reason it was the hardest problem is because people weren't sure whether to prove one way or whether to prove the other way, because it's not enough just to say the answer is yes or no. I'm not going to tell you what the answer is, because I don't want to spoil it for you. If you find this interesting, just Google me on YouTube or something like that. Google me on YouTube. That doesn't make any sense. Oh, actually, it does make sense because Google owns YouTube. Anyway, but look me up on YouTube and look for this. There's some talk about massive numbers. It's at the National Museum of Math. And that's like a 2-hour thing where I go through this in complete detail. Okay, more questions. We had some fun talking about reverse psychology. So much fun that we talked about reverse psychology, where maybe there are infinitely many reversals. What else can we do? Oh, that's interesting. So I like what Xinhua Xing said. Get a clone and have the clone try to prove yes while you try to prove no. This is in fact the right way to approach any question like this. You see, if you have something you don't know how to do, you unfortunately can't get a real clone. But what you can do is you can say, I'm going to be switching in a disciplined way between spending some time trying to do it one way, spending some time trying to do it the other way. You can use this also not in situations where you're trying to prove an answer, but in situations where you're trying to solve a problem. It is actually very smart to go and say, I'm going to try a few different ways in parallel. Don't just get stuck on one track, because if you do, you might just get stuck and get nowhere. So yes, you basically want a clone, and if you don't have the ability to clone yourself, most people don't, then you just go and use part of your brain to think sometime on each side. Oh, interesting. Oh, this is nice. So there's a question about if numbers have no end, then why is there no such thing as infinite speed or infinite weight? I like this because it's getting to a notion of infinite and another notion of arbitrarily large. So let me write down your question again, because this is something that it took me a while, quite a while to understand too. And the wording of the question is important. So I'm going to write down the question, and then we're going to start looking at the words. If the numbers have no end, why isn't there infinite speed or infinite weight? Okay, now this question as written is something which I can give a physics answer to and a math answer to, and they're both interesting. The physics answer is the one which is just, well, there isn't an infinite amount of stuff in the universe. So you actually can't get to infinite weight anyway. Numbers, on the other hand, are concepts. They don't actually take up space. A number is just an idea. And so you can actually have really, really big ideas that aren't taking up space. They're not using atoms or anything like that. So that's how you could have very, very large numbers, but no infinite weight. The infinite speed, why can't you have infinite speed? That's also a physics explanation. Nothing can move faster than the speed of light. So it turns out that there's a very finite speed limit. It's called c, the speed of light. But that's the physics explanation. I instead want to talk about a math angle of this thing, because actually this is also interesting because it tells the difference between two mathematical words which at first seem like they would be the same but mean very different things. And I'm going to write down those two mathematical words. One mathematical word is infinitely large, or infinite. Let's just call it infinite. Infinite. That's the right way to go. One word is called infinite, and the other word is called arbitrarily large. Okay, now these two mean very different things. Infinite just means goes on forever. Arbitrarily large means that there is an example of something which is of at least any given size. And now let me give some examples of things that are the things that are infinite and things that are arbitrarily large. Okay? So I'll make a sentence with arbitrarily large. The sentence is, well, let me use the word arbitrarily long. Well, it's like arbitrarily big, right? So I'll still use arbitrarily large. There are sequences. Let's call it decreasing sequences. Decreasing sequences of positive integers that are, it's going to be arbitrarily long. Arbitrarily long. Okay, so this thing I used arbitrarily long instead of arbitrarily large, but it's the same notion, right? It's that for any length that I want, there is a decreasing sequence of positive integers of length, at least that's that length. Does this make sense to people? Like, for example, if you told me, hey, show me a decreasing sequence of positive integers whose length is 50. Oh, I have one for you. It is called 50, 49, 48, 47, 46, 1. So I gave you a decreasing sequence of positive integers of length 50. If instead you told me, no, 50 is too small. Give me a decreasing sequence of positive integers whose length is 1 billion. I'll tell you, that's easy. 1 billion. I should have chosen a more convenient number. 1 billion. 999,999,999. 999,999,998. All the way to 1. And that's a decreasing sequence of positive integers whose length is 1 billion. And then you tell me, all right, give me a decreasing sequence of positive integers whose length is a googol. And I'll tell you, yes, that's easy. A googol? How do you say a googol minus 1? I guess you'd say a googol minus 1. A Google minus 2. All the way, all the way to 1. Oh, you guys are great. A Google minus 1, right? So if you can see, this pink statement is true. There are decreasing sequences of positive integers that are arbitrarily long. Arbitrary means you tell me any number, I'll give you something that is that number long. But does that mean that there are decreasing sequences of positive integers that are infinitely long? You see, infinitely long means that it really goes forever. In fact, there is no decreasing sequence of positive integers that is infinitely long. Every decreasing sequence of positive integers is not infinitely long. You see, the reason is because when you play, yes, thank you. So this is the question that that we're answering, right? The idea of infinitely is that you have one sequence, and that one sequence just goes on forever. The idea of arbitrarily long is, hey, you tell me how long you want it to be, I'll show you a sequence. You're basically coming up with lots of sequences, and each sequence is longer than the previous. But there's not one sequence which goes on forever. So this is the difference between infinite and arbitrarily large. And so in this particular question, you see, the numbers have no end. It is true the numbers have no end. Numbers have no end means numbers can be arbitrarily large. You tell me anything that could be the end, I'll tell you, no, there's something beyond there. That's what that means. This is arbitrarily large. And over here we have the words infinite. So I just wanted to use this to show the very important difference between saying something like if the numbers have no end, meaning if there's arbitrarily large numbers, how do you know about infinite things? And so even from a mathematical perspective, you don't get that. Okay, more questions. What can we do here? I see somebody said also numbers have no starting. It's true, numbers have no start and no end, because minus infinity and plus infinity, they don't give you anything. What can we do here? I'm looking to see, I see that people are discussing various kinds of jokes. Let's see. I want to see if I can hit another math problem. Oh, okay. Right. So I saw somebody asked a question. It's back to, wait, let's see this. Okay. So I'm looking through all this chat to go and try to see what are the different kinds of questions we'd have. And I see Philip Neller has asked a question which is about randomly walking. It seems to be Bob the cat is back. So this is about Bob the cat walking randomly on a grid. Because previously we talked about what happened if you had Bob the crazy cat walking on a track, so going forward and backward. And the question is, what happens if Bob the cat is walking on a grid? Walking on a grid means there are 2 dimensions now. Bob is going to randomly walk for 5,000 steps. Maybe Bob will go up, maybe to the right, maybe up again, maybe to the left, maybe down, right? You're just kind of walking around. And the question is, Bob the cat walks randomly for 5,000 steps. Where is he? So this is a question that's really just asking what's going to happen if I try to do something like this. So, cat the Bob. Bob the cat. Bob the flying cat. There's a 3-dimensional version of this as well. But if you're going to try to do the 2-dimensional version, what happens is that we already did the 1-dimensional version. We know what happens when we're only talking about moving left and right. And the 2-dimensional version is sort of like this. It's like Bob the cat first flips one coin to decide, am I going to move horizontally or vertically? And if it's horizontally, Bob the cat does his horizontal stuff. And if it's vertically, Bob the cat does its vertical stuff. So the way you can think of this is that each turn, each move, Bob the cat has a half chance of moving horizontally and a half chance of moving vertically. Now, each of these problems actually can be solved independently. Independently means I actually can tell you what happens if I just think of the horizontal stuff and don't even worry about the vertical stuff. Because it turns out that Bob the cat is going to take approximately 2,500 of the horizontal kind, approximately 2,500 of the vertical kind, but not just approximately that. You can also say approximately like plus or minus about how much. It turns out that Bob the cat is going to take the top one is about 2,500, which is about half of them, plus or minus. Now there's some square root NPQ. This is something about statistics. So you'll take about square root of 5,000 times 1/4. That's like about how much the error is going to be. Error meaning it will be about half of them, plus or minus some amount. And the plus or minus isn't just either minus or plus. It's like somewhere in between and maybe up to a little bit extra. This is like if you flip a coin exactly 5,000 times, you're going to get 2,500 heads on average. But you'll generally have a little bit of fudge factor in the sense that it's not exactly right. And the amount of fudge you have is about this big. And how big is this thing? 5,000 times 1/4, that's the square root of 1250. Does anyone know what's the square root of 1250? I vaguely remember 1296 is something. I don't know if 1296 is a perfect square or if it's a perfect cube, but 1225, that's 35 squared. So this should be about like 35, 36. Yeah, it's probably around 35 or 36, something like that. Yeah, but I'm saying that somehow you're going to have 2,500 plus or minus like around, it's 35.35, like around 35-ish, which by the way is very close to 2,500. So you're basically getting about 2,500 of this kind and about 2,500 of that kind. But in each of those kinds, then it becomes just what happened when Bob the cat moved in that way. When Bob the cat moved in this particular way, then Bob the cat was going to move like they would be about at 0 because they would have about the same number of lefts and rights, but the amount of error they would have is again the square root of 2,500 times 1/4. And that's about 25. So what we're finding out here is that you basically will find out that Bob the cat, well, let me write that down again, right? So now let's look at the first kind. This first kind is going to be about 2,500 random steps that are either left or right. And if you're going to do this many random steps, then it turns out that the amount that you end up balancing, like how far you are from where you started, your distance, horizontal distance, from, let's call it x equals 0, because we have an x and a y coordinate. So the distance away from x equals 0 is about, it's going to be off by, like every time you have an extra plus, sorry, if you have an extra, if the number of things that go in that direction is 1 extra, then you actually end up, wait, is that how I want to put it? Yes, if the number of things that go in this direction is 1 extra, you actually end up 2 in this direction. And that's because you changed one of this into this. And when you change one of this into this, you actually get pulled over this way by 2. This is like actually what we talked last time with Bob the random walking cat. But it'll be about 2 times, and now it's the square root of about 2,500 times 1/4. And so that's going to actually be about 50. So what I'm finding out is that somehow, as Bob the random cat is walking, the way you think of this is that you split apart the horizontal motions from the vertical motions. The horizontal motions and the vertical motions, both of them are around 2,500. And when I have 2,500 plus or minus 35-ish, I can say that's really about 2,500. On the other hand, over here, I was saying it's basically 0 plus or minus 50-ish. Now 0 plus or minus 50-ish is not exactly 0 if I think of things like proportionally. Proportional is how you think of it, right? If I say I'm going to have 0 plus or minus 50, well, it's not safe to say that then that's really going to be 0 multiplied by some very small percentage error. But up here, we're safe using a percentage error because whatever this number is, that's what goes into here. I know this is actually pretty sophisticated, so I'm not going to go and dwell deeper on this. If this made sense to you, I hope that's useful to you. But my bottom line is that somehow it looks like wherever Bob started, Bob's going to end up somewhere around 50 units, within 50 units of left and right, and around 50 units of up and down. So Bob's going to be in some kind of not too far away from where Bob started. Even though Bob took 5,000 steps, Bob's going to be somewhere like about 50, within 50 steps left, right, and within 50 steps up, down from where Bob started. This is basically showing that if you have a problem like this walking in 2 dimensions, you can sometimes think of it as 2 one-dimensional walks. What else can we do? He jumped. Paperboy wants to talk about 4-people chess again, but we did last time. It's the same thing. 4-people chess is the same deal as last time. I encourage you to go and play Bug House if you enjoyed that discussion. Can I explain stars and bars? Cleric, thank you very much for asking. That's actually something which is it's actually more of like in the course stuff that we do. So I'd prefer not to do that here. The good news is if you Google it, you can probably find out. But I prefer generally not to talk here about things that we already have in our online course because somehow that's not necessary. And also, if it's in our online course, it's probably in other courses too. And so I'd like to talk about weird things here that you can't find in courses. A plate. I'm not sure what that question is. A plate. Presumably you guys are talking about some kind of riddle. Let's see. Oh, Brian Lee! What is the probability that my problem will be picked? 1. I just picked it. You see, this is a funny thing. Like, what does it mean? What is the probability that something would happen? In some sense, it's almost philosophy, right? It's like, if it happened, it's 1. If it didn't happen, it's 0. For example, if I didn't pick your problem, then the probability it was picked is 0. But you asked what's the probability that my problem would be picked. And now if you're asking what's the probability that it would be picked, the way to think of this is that if I want to make an estimate, it has something to do with whether the problem has some interesting mathematical content. If your problem has a lot more interesting mathematical content, then it's more likely to get picked. But on the other hand, if it happens to be kind of fun and interesting, I'll just like enjoy watching it slide by, and hopefully everyone else does too. Eric Feng, I love your question. The question was, will you answer no to this question? Will I answer no to this question? I think I'm stuck. What's the right answer to that? Will I answer no to this question? Will you answer no to this question? I won't. How does that answer work for you? So the question was, will you answer no to this question? And my answer is, I won't. Okay, you can use that next time. Maybe it's not quite right because, maybe we could give a definite, we should give a definite answer. Don't just go maybe. I was actually, by the way, thinking of saying maybe, but I was like, maybe doesn't work that well because it's like, come on. If you said maybe, you're also wrong because like you didn't. So the correct answer to will you answer no to this question is I won't. Okay. Those questions are all funny. They all remind me of stuff like I used to go around the country and the world giving these talks, and at some point I sometimes said into the microphone, "Hey, can everyone hear me?" And I realized that was completely pointless. It's like, come on, if you can't hear me, please let me know. Doesn't work. Okay, let's keep going. What else can we have here? More questions. Okay, now we're getting into these paradoxes. Sophia Tang asks, and now Sophia Tang is very, very precise. She put in front, true or false. You insist that I have to answer true or false. This statement is false. That's a tough question. Here's my answer to that. And I'm not making a joke anymore. This is not a joke answer. this is one of these classic paradoxes that makes you look at it and be like, wait, how can that be? Because if the statement is, if it's true, then it's false. And if it's false, then it's true, right? So this is an example of a statement. Oh yeah, we already did this paradox you're saying. Well, I want to give it maybe another angle on this. I don't remember if that's what I said last time. But the angle on this I'll give is that this is just not a reasonable statement. You see, because I can tell you there's a similar problem. Here's what I'll say. The answer is the same as, here's my answer. The answer is the same as this statement. True or false? Q, Z, W, A, B, X, W, T, 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 7, exclamation mark, minus, smiley face. Same answers. So the situation is that somehow this thing, does anyone know if this is true or false? So the bottom line is like, this just doesn't make sense. I don't think there's anyone here who understands what I wrote, because I don't either. I have no idea what this means. It's just nonsense. And so if I write down nonsense, of course it's neither true nor false. It's just nonsense. It doesn't make sense. And so the situation about this statement is false is the same problem. It's like somehow it doesn't make sense. Okay, more questions. True or false? What is your favorite color in the alphabet? Oh, you know what? You know what that makes me think of? This is a famous thing. Maybe some of you have seen this before, but I hadn't seen this when I was at a younger age. Here's a major challenge for you. Read these really fast. If the game becomes there's like two different kinds of games. One kind of game is called read these words really fast out loud. If you read these words really fast out loud, that's one thing you can do. The other kind of game you can play is don't read the words out loud. Say the color. Say the colors that you see out loud. Both of these are actually quite hard. If you try to say the colors you see out loud, you're like pink, green, blue, yellow, white, maybe. I mean, but if these are long, if there's like a long list of this stuff, then it's actually quite hard to do this. So you asked me about like, what's your favorite color of the alphabet? I'll say that when you put these colors and alphabets together, it's famous, and somebody mysterious has even done this before. It's mysteriously difficult. Mysteriously difficult. Actually, another thing along these lines, just showing how, you asked about colors and alphabets and there's meanings. Color is harder, thanks guys. But here's something else that's interesting. If you look at this, you can actually kind of figure out that it says mysterious. Okay, sorry. If you read a sentence and the words are all like scrambled in the middle, you actually sometimes can figure out what each word is. It's a really, really funny thing, and you can try it sometime. You just go and take a sentence, and each of the words you do some jumble, or you should get someone else to do it for you. Do that, and give it to you, and you'll find out that you mysteriously can read it. So this is just like funny stuff about how we humans read words. All right, more questions here. Mysteriously difficult. Can I evaluate parentheses -3? Not sure what that means. Let's keep going. Okay. Batmobile. I'm a genius at math, but I want to be a doctor. What should I do? Well, there's two kinds of doctors, There's the kind of doctors that help people, like heal people, and there's the kind of doctors that don't. I'm one of the other kind. The kind that don't. So I think maybe that's not what you wanted to be. Like you said, you're really good at math. If you go and become a doctor, a PhD in mathematics, you could also be a doctor. But my guess is that's not what you want. You want to be a real doctor who heals people. And in that case, if you want to be like a medical doctor and you like math, that's not a problem. Actually, if you're really good at math, I've observed that it makes it so that you can learn things better. You're more efficient at learning things. The thing is, if you're good at math, you're pretty good at reasoning and thinking. And the hard part about getting into medical school is probably going to be some of these extensive biological and anatomical extensive facts that you need to know. But facts are easier to know if you understand where they come from. And so use your mathematics understanding to, I guess, systematize biology and anatomy. And then you'll have a better time trying to pass all of those tests. It's actually good that you want to be a medical doctor. I don't think everyone in the world should become a math doctor or a PhD in math. The world needs medical doctors too, especially right now. And so, good, I'm glad you want to do it. And never think that somehow being good at math means that you can't be good at being a doctor. In fact, if you are good at math and you also become a doctor, a medical doctor, you might even have some ways of helping people by coming up with new observations. You might come up with new ideas of how to do things in the hospital or in the clinic. In fact, you can even become a double doctor. I don't know if some of you know this, but there are some people in the world who go through all of the schooling to get 2 kinds of doctorates. Those people get both the MD and the PhD. Now, of course, usually the MD is medical, and usually the PhD is something like biological PhD. But there are people in this world who are doctors, double doctors. I'm not one of these people, but maybe that's what you'll want to do someday. Okay. Looking for a good question. What can we do here? Double doctor sounds tiring. Well, some people do it because they think it will make a huge impact. Let me tell you a story about somebody I know who wants to do a double doctorate. And that person actually lives in my city here in Pittsburgh. It was very interesting what the person said. The person said that, first of all, they were studying both the medical doctor and the PhD. Actually, their PhD was in machine learning and things related to neuroscience or artificial intelligence. And the reason they wanted to have both is because they felt that if you wanted to have some way of doing experiments in neuroscience, the easiest way to do that is if you actually also were working in a clinic. The reason is because, actually this is the way he explained it. The way he explained it is, suppose you want to learn about physics. You'd really like to just go to a pool table, like the table with all those balls on it. If you want to learn about physics, you should go to a pool table which has a bunch of balls. And if you want to, not learn about physics, we're talking about research now. If you want to know how physics works, you go to a pool table, then you get this pool stick, and you start banging balls, and you watch them all bang into each other, and after a while you figure out the laws of physics. Right? That's how you do research in physics. You go and get something, and you do an experiment, and you jostle stuff around, you bang them, you blow them up, you smash them into each other, and after a while you figured out the laws of physics. So what he said is, he wants to figure out how the brain works. But you're not exactly allowed to just go and say, I need to figure out how brains work. Let's go and smash some people's brains together. That's just not legitimate. You cannot go and say, if I want to know how the brain works, I will just go and randomly smash people's brains together. That's no good. So actually what he said is, if you're both a medical doctor and a PhD doing research in the neuroscience, because anyway you're doing brain surgery, while you do the brain surgery, you don't smash brains together, but you have the opportunity to just see what happens as you're doing the brain surgery itself. So his explanation was, if you really want to learn something about human brains, you would need to also be naturally doing something to human brains that's helping them, as opposed to just smashing them into each other. And so that's why he was going through all the effort to both become a neurosurgeon and also a PhD at the same time in this neuroscience and machine learning. Okay, more questions. We got one more. Yeah, that's a good idea, Joshua Wang. I'm glad you think that's a good idea. Actually, when he gave me that explanation, that made a lot of sense. And I was really glad that there was a person like that who was going to try to learn how brains worked. Let's see. What can we do to be the closing question for today? Okay, so maybe I'll close with something here, which I saw somebody asking, what advice might I have for an International Math Olympiad aspiring contestant? And I'll give the answer to be more general. What would I give as my advice to anyone who's aspiring and doing these mathematics competitions? As certainly many of you might be involved in, and certainly by next week, as we're doing the Math Counts problem reviews, we'll probably have tons of people here who are all in that category. My advice I'd give you is those questions are good ways to make you smarter. Ultimately, your goal should not just be to win a contest. Winning contests is kind of pointless. You just win the contest and then so what? The goal is to do something useful later. Whether that useful thing is to figure out how the brain works by not smashing brains together, but by, actually having a legitimate idea of what to do. Or maybe your contribution later is going to be working in a job where you come up with some interesting ideas that the world then sees through the products that you make. So the idea of these competitions, do them for one purpose. Do them to go and challenge yourself and to go and see if you can do more today than you did yesterday. And that feels good. And don't worry if you win or lose with other people. Other people will always be around. But you are a benchmark that you can always compare against. So my advice is always compete against yourself. If you liked what you saw today, please do tell more people. Especially, please tell people about next week's Wednesday, Thursday, and Friday Math Counts chapter competition review. If you go to if you go to our live stream website, poshenloh.com/live, we already list out which questions we're going to talk about each of these days. Please do tell people, because then we're going to have fun interactively discussing these different ways to solve problems with many more people. And as you may know, we have this weekend live stream. It's going to be tomorrow at 8 o'clock p.m. Eastern Time. And as usual, I will go and find some math problem that may be relevant to my life at this moment. I don't yet know what that problem is. I'll have to find it. But then we'll talk about that. And then we'll have a free Q&A, free-form Q&A about all kinds of things that aren't specific questions. Why am I pointing at this? Which aren't specific questions like this. Also, if parents or coaches are interested in joining that weekend live stream, they're of course welcome, because those discussions are more general. All right. Well, I've had fun for this week talking to all of you. I wish all of you a very happy rest of your Friday. And maybe I'll see some of you tomorrow. Take care.